Okay, so we're going to give a new program a go and see if I am not as frustrated and see if I can still write in all those handy dandy things. Okay, what we're going to do right now is just do some concept check questions. So this is going to be a relatively short video, but let's give it a go. I have a rod and it is next to a charged ball, and we want to know what we can say about the charge on the rod. Is the rod positive, negative, neutral, or is it a combination of those? So think about it and then come on back. All right, so it's attracted, so we know that it is either of two things. Remember, it's neutral and being polarized, or it's negative. So then the answer to this would be both B and C, or either B and C. We don't know. Now we're going to go back into this concept of polarization in a little bit more depth. And one of the things I want to emphasize to you, and I think with all the technical issues, the lecture might have been lost, so I'm going to repeat it just in case. Let's go back, here we go, to this slide. And if it's a repeat, I apologize, just fast forward and ignore this. But when we were doing the first lecture on Friday, and I was talking about rubbing the rods, one of the things I described was what you're seeing here, where I have a charged rod and I'm bringing it near to this bulb or just a round circular, of course round is circular metal plate. And if I bring a positive rod, I am drawing electrons up towards the top of the bulb. And in doing so, what's left off at the bottom is these positively charged, generally they're like gold leaves just dangling there. But the positive charge, you can actually see the leaves separate. It's kind of cool. If I did the opposite, if I did it with a negatively charged rod, you would see those positive charges at the top as all the electrons flee down to the leaves. And once again, you see the leaves separate. When I bring something close to another, and I induce that behavior, that is induction. There's no transfer of charge. It's just a motion of charge or an attraction between two things. I can also charge something through conduction, which is if I touch something that is charged with, something charged to something not charged, then I'll have this even distribution of those charges. I can bring charged rod next to two touching items and induce polarization between those two touching items, because the neutral charges, remember, everything's going to go is spaced out as it possibly can, so it would spread its wealth, if you will. And so if I separate those two things, now I've induced a charge. Take my wand away and I have two things with excess charges. It's pretty cool. The picture on the right, I just like that for kind of the bringing to the foreground the impact of distance, and then by extension the forces that would be experienced when you do a polarization. So as you can see there, you have the positive charges on the bottom of the plate because the negative electrons have been attracted to the positive wand. The repulsive force between those positive charges, because of the bigger distance, is going to be much smaller than what the negative charges are experiencing. So that's pretty cool. All right. I bring all that up because now let's apply this concept of charges moving between things or not moving between things and see how well that's kind of clicking with you. So I have two metal spheres and I'm bringing a charged rod next to it. The charged rod is removed so it doesn't touch the metal spheres, and then the spheres are separated. So what do you think the charge on the spheres will be after I remove the rod and separate the two spheres? Think about it and then come on back. Okay, so hopefully you concluded that the charge on both spheres would be 0. And the reason for that is I bring the rod next to the two neutral spheres, so I am indeed inducing the negative electrons to go onto sphere 1 and get closer to the positive charge, which means that I would have an overall positive charge on sphere 2. But as soon as I take away that rod, the charges just redistribute themselves. So now I have two neutral spheres once again, so when I separate them, nothing changes. Everything's the same. Okay, now I'm going to do the same thing, but this time I'm going to bring the charged rod near, and while the charged rod is near, I'm going to separate the spheres. So what do you think is going to happen this time? Take a look at your options, and then pause, think about it, and come back. Okay, so let's see. It's kind of, I accidentally gave it away in the previous slide question, right? So I brought the charged rod near. The electrons rushed into the first sphere, sphere number 1. That means that if I separate them, after I've done that, now I have excess electrons on on sphere 1 and a lack of electrons, so a positively charged sphere 2. Okay, let's ramp it up. This will be our last little check. And the one thing I want to say is don't think of these in terms of nanocoulombs. It's the only thing I dislike about this example. Think of them as in terms of like a electron. So the one on the sphere P would be missing 4 electrons. Sphere Q has 2 extra electrons, and sphere R has 1 extra electron. So here's the process we're going to go through. P is going to touch Q. Then I'm going to separate P and Q. Then Q is going to touch R. And then I'm going to separate Q and R. And I want to know what the charge is on, what am I asking for? On R, when all is said and done. So work that out, and then come on back, and let's see what you get up, what you came up with. Right? So the answer is 0. And one of the ways to think of that is I have 4 here, a positive 4 here, so I'm missing 2 electrons, and a minus 2 here. So let's see what happens if I give those extra electrons on Q when P and Q touch to P. So if I do that, so P and Q touch, and Q gives 2 electrons. What am I left with? Now I have a P with a +2 and a Q with a 0, right? It's now neutral. It's given up all of its electrons. So that's not equally balanced. It wants to be as balanced as possible. So to make that happen, we're going to have a little electron shuffle again, and I'm going to end up with a +1 here and a +1 here. So what happened is the 0 gave up one of its electrons, right? And it balanced out with a P. So now we have a deficit of electrons on both P and Q. Now Q touches R. Touches R. Well, when that happens, I now have Q with a +1 and R with a -1. So R has an extra electron. It's going to give its extra electron to Q. So after, they're both neutral. Both neutral. This is a good exercise to go through again on your own and make sure that you understand how things are moving. Conduction and induction. I mean, knowing the names was handy, but understanding when electrons are transferred versus when we're just inducing a temporary polarization is an important concept to have in mind. All right, so let's see if this thing worked. See if I can find how to stop the recording. Oh, this is fun.